Okay, so we talk about Euler's theorem here. So let us just write the statement of the Euler's theorem. Euler's theorem is telling let n and a be two integers such that means GCD of n is 1, then a to the power phi n is basically congruent to 1 mod n. So, this is the statement of Euler's theorem. So, we take a integer n and we take a integer a such that they are relatively prime, then GCD of this is 1. So, if you take n to be prime, if n is p which is prime say, then this is then phi to the power p which is basically what, with this we know phi p is p minus 1 phi function, then this is basically 1, this is coming from Fermat's-Little theorem. But that this is a particular Fermat's-Little theorem is a particular case of Euler's theorem, but Fermat's-Little theorem was invented before this Euler's result came into the literature. So, we are going to prove it in general way that this phi of this is basically phi of n is congruent to 1 mod n. Okay, so how to prove this? So, to prove this we need to take help of what is called reduced residue class, the R. So, okay, so we have n is the number integer. So, we know this z n star, this is basically set of all integer which are 0 non-zero positive integer which are less than n such that they are co-prime to n, this set, and this cardinality of this set is basically phi of n, and this set is also denoted by R. This is called reduced residue class modulo n. Okay. So, now if A is independent with n, independent means co-prime to n. If A is co-prime to n, then if we define this AR is basically A into R, where R is coming from this set. Okay. Now, we have seen this AR is basically R, since A is co-prime with n, because if you take any two, so this set is basically what? So, this set is basically this set is basically, if you take any two element from this set, say n a and which is n a which is congruent to say m a mod n, n is there. So, we cannot use n. So, x y we can use. So, suppose we take any two element from this element here, say x y. So, x a is congruent to y a mod n. Now, since this is independent, this inverse this imply A inverse exists mod n, and we can find this inverse by extended Euclidean algorithm. So, we can multiply A inverse both sides. So, this will give us x is congruent to y mod n. So, any two element here are, so these elements here are basically congruence of the elements over here in some order. So, basically AR is equal to R. So, what we do? We multiply all the elements of AR. So, we multiply all the elements of AR. So, So, this is basically we denote by R star, sorry. Okay, so AR is basically R. So, now and the number of element over here is, we know this is the phi n. So, if we multiply all the elements from this AR, so this will be of the form a to the power phi n into r. R is coming from this R, and this must be congruent to, since so this is the all the element we are multiplying from this set, okay, and this must be equal to phi of R, because these two set are same, may not be in the exact order, I mean the order we are having. So, maybe in the different order they are under congruence operation. So, this is the result under mod n. Okay. So, now here in this, so all the elements over here in R are basically in co-prime with n. So, that means all the product is also basically co-prime with n. Okay. So, that means this inverse exists under mod n. So, we can multiply this by this inverse of this. So, this we denote by say z. So, this is basically, let me just so this is basically we have a to the power phi n into z is congruent to z mod n. Z is basically R. Now, all the elements over here is, if R belongs to capital R, then R is independent with n. So, that means all the elements are independent with n. So, that means Z is this independent, independent means relatively prime. This symbol we use for relatively prime or co-prime. So, that means Z inverse exists. So, we multiply Z inverse on both sides, we will be getting phi n is congruent to 1 mod n. So, this is the Euler's theorem. We prove the Euler's theorem. So, this is true for any integer n and integer a such that a is relatively prime with n. So, this condition must be there for this result to be hold. Okay. So, let us take an example. So, this example say we take n is equal to say 21. Okay. So, then what is phi n? Phi n is basically, so 21 can be written as phi of sorry, this is phi 3 phi 7, phi 3 and 7. So, this is, these are in relatively prime. So, we can use that. Now, these two are prime numbers. So, for prime number we know this result. So, this is basically, so this is basically 3 minus 1 into 7 minus 1. So, this is 2 into 6, which is 12. Okay. Now, we take a which is basically relatively prime with 21. So, if we take a is equal to 5, then a to the power phi n is basically, this is basically 5 to the power phi of 21, this is 12 basically, this is basically phi of 21, phi of 21 is 12. So, phi of 21 which is basically 12, and we can easily verify that this is congruent to 1 mod n. So, this is an example of Euler's theorem, and we have seen the Farmer's little theorem is a particular case of Euler's theorem. So, this we will use in many cryptographic protocol like RSA, many cryptographic algorithm RSA. So, to prove correctness of RSA, we need to have this theorem in our hand. Okay, so, now we will define what is called quadratic residue modulo some prime p. So, we define the term quadratic residue. Quadratic residue modulo p, where p is a prime. Okay. So, how to define this? The definition of the quadratic residue. So, let p be a prime number and a be an integer Okay. Now, we define a is called integer is called a quadratic residue, mod p if and only if the congruence equation y square equal to a mod p has a solution in ZP. Okay. So, and here a must be a is not congruent to 0 mod p. So, that means a is not a multiple of p. A is congruent to 0 mod p means a is either p, 2p, 3p like this. So, we are not allowing this. So, a is not a multiple of p. Okay. So, that means a has a square root. So, that square root is basically y. So, a has a square root and that is basically y. Then we call, if this equation has a solution, then we call this as a quadratic residue. This a is a quadratic residue mod p, and so this is quadratic residue. Now, when we say it is a quadratic non-residue, if this equation has no solution, if a is not a multiple of p and a is not a quadratic residue, mod p, then a is called a quadratic non-residue mod p. A is called a quadratic non-residue mod p. Okay. This is if a is not a quadratic residue, then we called a is a quadratic non-residue. Okay, we will take some example. So, suppose we take a prime number p, say p is equal to 11. Okay, so there are many cryptographic algorithm which are based on this quadratic residue. So, this has good importance in cryptographic protocol. So, let us take P to be example. Okay, so let us take P to be 11. So, we are in Z11. So, we are talking about quadratic residue under mod 11. So, we are in Z11. Okay, so, now if we take the possible Y's. So, basically we are looking for a quadratic residue in Z11 basically. So, we are looking for A such that y square equal to congruent to mod P. So, then A is a quadratic residue and this y is sort of square root of A, kind of square root. We are square, as if we are squaring A, we are finding the square root of A. So, that means we are looking for possible y's, so that we can, so if y exists, such a y exists in ZP, then we call A is a quadratic residue. That means A can be square root, I mean A has a square root. So, A is called quadratic residue. Okay. So, if we try for all possible y's kind of things. So, this is basically 1. So, these are all under mod 11 operation. So, plus minus 2 square, this is basically 4, plus minus 3 square, this is 9, plus minus 4 square, this is 16, then 16 mod 11 is basically 5, plus minus 5 square is basically 25. So, 25 mod 11 is basically 3, plus minus 6 square. So, these are the possible y's, this plus minus 5 plus minus 6 is basically 36, 36 mod 11 is 3, plus minus 7 square is basically 5. These are all under mod 11, plus minus 8 square, this is basically 9, plus minus 9 square, it is basically 4, plus minus 10 square, it is basically 1. Okay, so, these are possible y's basically. So, y if, so y must, so P is 11. So, y must come from this set basically Z 11. Okay. So, these are possible y's. So, that means these are the quadratic residue. So, basically this set 1, 2 is not there, 3, 4, 5, 9. So, this set is basically, this is, these are all the elements over here are set of all quadratic residue mod 11. So, these are all quadratic residue under mod 11. So, this is denoted by basically we can denote by QR 11, quadratic residue mod 11. Okay. So, that means remaining are the quadratic non-residue mod 11. So, any element, because 4 is a quadratic, 4 a is equal to 4, 4 is a quadratic residue mod 11, because for 4 we have a y. So, if you take y square is congruent to 4 mod 11. So, that means, yeah, so y is basically plus minus 2, plus minus 2 is basically 9. So, it is basically, so the y is basically 2 and 9. So, for this, so that means 4 has square root. So, these are the possible values of y. So, for this y, if you square it, then take the mod 11, it will give us 4. So, any element over here has a square root. Okay. So, now yeah, so this is the 4. If you take 5 also, for 5, so if you want to find out y square is congruent to 5 mod 11. So, 5 mod 11 means, so y, what is y? Y is either, So, 5 who is giving us 5, 4 and minus 4, 7 and minus 7. So, minus 7 is 4 basically under mod 11 and minus 4 is equal to 7. So, this is basically 4 and 7 which are coming from Z 11. So, these are all quadratic residue mod 11. Okay. Now, who are the quadratic non residue? So, the remaining set like 2, 4, 5 is there, 6, 7, 8, 10. So, these are our quadratic non residue mod 11, because if you take any, you say for example, if A is equal to 7, then there does not exist a y such that y square is congruent to 7 mod 11. So, there this system has no solutions, because there is no such y, there does not exist y in Z 11 such that y square will give us 7 mod 11. Okay. So, that means these are all quadratic non residue mod 11, and surprisingly the cardinality of these two sets are same, and this is true. In fact, in the later stage we will see that, even we will try to prove that this thing is true. So, set number of quadratic residue and number of quadratic non residue are basically these are same set. Okay. So, now we will have a Euler's criteria for a quadratic residue. So, it is a condition for A to be a quadratic residue. So, let us state this is a necessary and sufficient condition. So, this is basically by Euler. So, that is why it is called Euler criteria, criterion for quadratic residue. So, this is a theorem. This theorem is telling, the statement of this theorem is basically, so let P be a prime okay, and then say then an integer A is a quadratic residue mod P if and only if, this is the condition, if and only if a to the power p minus 1 by 2 is congruent to 1 mod p. So, this is the Euler condition for A to be a quadratic residue, that means A has a square root. Okay. So, this theorem is telling A will be a quadratic residue, that means A has a square root if this condition satisfies. It is in both the way, if and only if. So, that means this is the necessary and sufficient condition. So, this condition we will use to check whether a integer is a quadratic residue or not. Okay. So, let us try to prove this theorem. Okay. So, how to prove this theorem? So, there are two ways. So, first let us assume this is a quadratic residue. So, this is if and only if condition. Suppose, so first part is, let us assume this is a quadratic residue, then we have to show this condition is satisfying, and the conversely, let us have this condition, then we have to show the A is a quadratic residue. So, let us first suppose A is a quadratic residue mod P. Okay. So, sorry. So, suppose A is a quadratic residue mod P, then we have to prove this theorem, we have to prove this result. Okay. If A is a quadratic residue mod P, that means we have a y, that means there exists y in ZP such that y square is congruent to A mod P. So, that means we have a solution under modulus operation of P. So, that means there exists a y such that this satisfies, okay, and y is from ZP. So, now, so basically A is y square mod P. So, we have a to the power p minus 1 by 2. This is basically congruent to A is congruent to y square mod P. So, we will just write y square then p minus 1 by 2. So, this is basically y to the power p minus 1. Now, this is what? Now, y is from ZP. So, that means that means y is p is a prime. So, y must be co-prime with p. So, that means by Fermat's little theorem or the Euler's theorem, particular case of Euler's theorem, this is coming from Fermat's little theorem, this is basically 1 mod p. So, this part is done. So, a to the power p minus 1 by 2 is congruent to 1 mod p. Okay. This part is done. Okay. Now, the reverse, suppose this is true, then we have to show A is a quadratic residue. So, that we have to prove now. So, now we have to prove, we have to assume this condition is satisfying, and then we have to show the A is a quadratic residue. Okay. So, this is the conversely, suppose the condition is satisfying, suppose a to the power p minus 1 by 2 is congruent to 1 mod p. Okay. Now, so suppose this current, now we have to show that A is a quadratic residue. So, that means we have to get a y basically. Okay. So, how to get a y? Now, ZP, P is a prime. So, ZP star is a cyclic group. So, it has a generator or the primitive element, let B be the generator or the primitive element in ZP star. Okay. So, now, so A is an element from ZP star, basically we are looking for quadratic residue less than P, basically positive integer less than P. So, that means A is an element. So, A will be written as, so this B must generate the group. So, A is an element. So, B will be, A will be written as some b to the power I mod P for some integer, where I is an positive index. Okay. I could be 2, 3 something. Okay. So, now we will use this Euler's. So, we have this result, this is 1 mod P. Now, we will put here B. So, B to the power basically I into P minus 1 by 2 1 mod P. Okay. So, B is a generator. So, now this is, so that means this is a the order of B. Order of B means the B generates the group. Order of B means the minimum integer such that B to the minimum integer k such that B to the power k is 1 mod P, identity element basically. So, that means this whole quantity. So, this is giving us 1. So, this whole quantity, and we know the this ZP, order of ZP star is P minus 1. Okay. So, that means this must divides P minus 1, or P minus 1 must divides this. So, this must be a multiple of P minus 1. So, that means this must be some k into P minus 1, because P minus 1 is the order of the group or the order of the element B, because B is the primitive element. So, this implies I is equal to 2k. So, I is an even. I is an even number. Okay. So, since I is an even number, so we can take I by 2. So, that means plus. So, basically, so since I is an even number, I is basically 2k. So, if we take this b to the power I by 2, this is basically b to the power k. So, basically plus minus b to the power I by 2 at the solution of this at the mod p, obviously solution of this congruent system y square is congruent to a mod p. So, that means it has a solution. So, this implies A is a quadratic residue. That is it. So, this implies A is a quadratic residue. So, this is the condition to check whether a integer A is a quadratic residue or not. This condition, a to the power is congruent to 1 mod p. So, this is the condition to check whether A is a quadratic residue or not. Thank you. This is the necessary and sufficient condition. Thank you.